I guess it's hot everywhere. It seems Boston. Great. So I see that your slides are already projected. So I hope that
Yes.
everyone nice.
Yeah.
Great. So welcome everyone. It's a pleasure to have Huanbo Sun with us. And Huanbo is going to be talking about machine learning driven haptic sensor design. So Huanbo, recently defended his PhD thesis at the Max Planck Institute. And, before this, he was doing his master's and bachelor's from RWTH Asian University. And I think, Huanbo has done a bunch of exciting work around, not just designing sensors, but also, using them for control and trying to really take the whole system's perspective. So I'm pretty excited to hear more from you, Huanbo. So welcome and looking forward to your talk.
Okay, thanks, Agrafal, for your introduction and your invitation to this seminar talk. Hello, everyone. I'm Huanbo, and the current focus of my research is to design haptic sensors to give robots a better sense of touch. And wait a second, work. So a general self-introduction is I have a background in mechanical engineering with focuses on mechatronics and robotics. I mainly worked on designing a smart car, a bipedal robot, and a snacker robot. During my bachelor study and during my master study, I pursued the direction of medical engineering with a focus on medical robots and medical imaging systems. During my PhD study, I worked on designing machine learning-driven haptic sensors to give robots the better touch sensing capability. So today I will focus on introducing the haptic sensors I designed during my PhD study. My daily work is to sit in the lab and take care of this cute humanoid robot called Poppy. And inspired by biological systems, we think robots also need touch-sensitive skin to perceive the environment, where interactions are constantly involved and visual feedback is often included. So a common theme for surface haptic sensors is to integrate many small sensing elements. We name it Tactile and use massive wires to communicate with them. This is a common setting. So unlike other sensing modularities, such as our visual feedback or our sound feedback, haptic sensors need to constantly interact with the environment and thus have higher risks of being damaged with even either broken wires or sensing elements. The situation gets even worse when we pursue higher resolution with thinner wires and smaller taxons. So similar to humans, different robotic parts have different resolution requirements. For example, a fingertip needs extremely high resolution to sense delicate contact information on a very focused area of our fingertip. In contrast, a robotic limb doesn't need such a high resolution but large area coverage. So from the hardware perspective, both cases need numerous taxons. Technical challenges arise concerning the physical size of the taxons, as well as growing wiring and manufacturing costs. On the other hand, from the software perspective, sensors normally provide digital values. This is raw measurements from our computers, and these digital values is somehow not intuitive and not easy to understand, especially for a daily layperson. Thus, we need to find a way to extract useful haptic information from the raw measurements to describe the contact events, such as the contact locations or contact shape, force strengths, force distribution on the skin, or the force directions back and forth, etc. So during my PhD study, I set the goal to solve these two major problems. First, to design robust haptic sensors, and second, to deliver useful haptic information for small-scale and large-scale robotic parts. We propose using the super resolution technique to tackle the problems in the hardware design procedure and developing machine learning methods to extract useful haptic information. The whole study is grounded into 5 projects. There are 2 strategies tested for large-scale sensing, focusing on robust limbs and chest at the whole body coverage. There are also 2 designs for small-scale sensing, aiming at providing human fingertip-level sensitivity. Sensor designs include both hardware and software parts. In a common design flow, hardware and software parts are designed separately or iteratively. We provide a machine learning method to bridge the hardware and software parts and use it to guide future haptic sensor design from a systematic perspective. I will introduce the 5 projects one by one. The first one is called HapDef. It is designed for large-scale sensing that can localize and quantify multiple contacts on the sensing surface. On a large curved surface with a size, this one, of my forearm, only a few sensor units indicated as the orange dots are sparsely attached to the surface to measure the surface deformation. Using only 10 small sensors, we can infer the deformation of the whole 3D surface caused by double contacts, as showcased here. The sensor unit we use is a strain gauge. The strain gauge changes its resistance when we bend it. The whole system works in a way that a single contact on the surface causes several strain gauges to respond. As shown here, the unique response pattern of multiple strain gauges enables data processing methods to extract contact information. So these 2 bumps are for 2 contact positions with different applied force strengths. We then built an automatic testbed to collect single contact data and train a machine learning model to directly predict the contact location and force strengths for single contact at runtime. The method can localize and quantify the force strengths very accurately, as shown here. So there are 3 machine learning models trained to predict the contact position, and also we have a force torque sensor to measure the contact force as ground truth, as shown in this bar. The predictions on the right bar shows a good match with the prediction with the ground truth, the force torque sensor. As shown here, the testbed is specified to collect single contact data. How can we extend the system for multiple contact detection purposes? Considering the complexity and cost of building a testbed for calibrating multiple contacts, we pursue another path called transfer learning. We first built a finite element model to collect multiple contact data in simulation and train a machine learning model called Reconnect that maps the simulated sensor values here to a displacement map shown here. A displacement map describes the deformation of the entire sensing surface for multiple contacts. We then use the built testbed in the real world and the finite element model in simulation to collect single contact data with the same contact condition and train a machine learning model called TransferNet to correlate the real system with the simulated model. As proven in the showcases, the proposed method can jointly consider the single contact and multiple contact information from different data sources, one from the real testbed and one from the simulated finite element model. Based on the displacement map, we can do post-processing to extract the contact location and force strengths accordingly. Different colors indicate different contact locations, and also the size. The bigger the sign indicates stronger applied force. In summary, the sensor can achieve the sensing performance similar to a human palm. The design ensures robustness with a simple manufacturing procedure. It has a high update rate and with low energy consumption and material cost because only a few sensor elements are used. Compared to a hard structure like this one, a soft compliant sensing surface can ensure safer interactions. Thus, we also consider another type of sensor named ERTac. It wraps a large surface with a whole piece of soft conductive fabric. It has multi-layered structure with only a few electrodes assembled on the surface, as shown at the green dots here. We insert current in one pair of the electrodes and measure the voltage difference between other pairs of the electrodes. By switching the current injection pairs and the voltage measurement pairs in a combined manner, we can reconstruct the conductivity over the entire sensing surface. This is a technique called electrical impedance tomography. I will mention this technique later in my talk. Once an object contacts the fabric, we can measure the conductivity changes. Based on the predefined force working range, we choose the material with adequate elastic modules, especially for the conductive form. And then we built a test bed with capabilities of collecting up to 6 contacts simultaneously. The 6 indenters, shown as the light green dots, with load cells to sense the ground truth of the force strength, are assembled on a disk. A DC motor controls the relative position of the 6 indenters on the disk, either closed or open or in between. The disk is moved above the sensing surface using a linear stage to collect multiple contact data. And machine learning models trained on the collected data takes voltage measurements as input and output a force map. The force map shows the number of contacts, the contact locations, the force strengths, and also the contact areas for multiple contacts in one shot. This is the force ground truth measured by the load cells, and the predictions of the trained machine learning model show a good match with the ground truth. As you might notice here, the prediction.
Maybe a question, Huanbo. So are you measuring the magnitude or just the location over here?
This is like magnitude also for strength. There are different colors, right? The light color means the higher strength.
Okay. And this is mostly normal force, right? This sensor doesn't
normal
do
force.
shear force.
This is normal force for large scale sensing. For shear forces or for detailed information, we think small scale sensor needs this, but large scale we ignore the shear force detailed like force distribution about it.
Okay. Okay.
Yeah, and also here the predictions has a geometry constraints on a hexagonal shape right here. Because we collected data using a test bed with a hexagonal disk. This is the typical data insufficiency problem that machine learning pipeline has to deal with. And then how can we solve this kind of problem? In addition to the data collected from the test bed with a hexagonal shaped disk, we built a multi-physical model in simulation to collect more diverse, copious good data. And then a similar transfer learning method is used to integrate the raw voltage measurements into real-world haptic value, a force map for multiple contact detection. Using only 28 electrodes for a sensing surface with the size of my shirt, the sensor can detect up to 6 contacts simultaneously with only 14% localization error, 70% force error, and 10% diameter error. The proposed sensor design strategy can be used to many applications with scalability. It only matters with the how many electrodes we use. And also it's soft and robust due to the nature property of the fabric materials. It is easy to manufacture with low material cost. It can be wrapped on many 3D sensing surfaces to realize large area coverage. So these two sensors can achieve high resolution sensing using only a few sensing elements, either these strain gauges or using electrical impedance tomography technique.
Maybe a quick question. So what is the durability of these sensors? How long can I run experiments for?
This one has used for 4 years. And another one, we recently published a paper, but we haven't tested the durability of it. But the first one is specified for the application in industrial robots, because the industrial robot has the metal shell, right? Typically like Panda or Kuka, they have the metal shell that we can place the strain gauges just internally, and then this can be very robust.
I see. And is there a reason to believe the conductive fabric, the second sensor, might deteriorate in some time, or do you also think it is going to be robust?
It will have the performance will have a drop, or we have to calibrate them because the fabric will stretch, and then like our clothes, it will not recover to the original shape or original conductivity, right? So this has a long-term calibration procedure in mind. Yeah.
Okay. Thank you. And maybe one more. So the material that you use to make these sensors, if you brush across like something like wood, right? Will the material get weared off, or will it sustain itself?
For the current material we use, we didn't test it, but it's like the property might also act similar like our clothes.
I see. I see.
Yeah.
Okay.
Yeah. So all these two designs using a few wires and a few sensing elements can achieve high resolution sensing. But how could this be possible, right? And is it just because we use machine learning methods? So do we have a physical explanation about this for the sensor design? Well, and also when designing sensors, we always encounter the following questions back and forth. We have to make decisions. First, which physical quantity to measure? We have like resistive, capacitive, optic, magnetic sensor types that or property that we can measure. And also in the end, we need to build a physical sensor. How to structure it from the mechanical perspective, and which material properties matter most, and which material to use to build the sensor. And did I collect enough good data for calibrating the sensor to the other useful values? Or is my data processing methods good enough to dealing with the noise in the measurements? All these questions gathered together, and I was wondering whether they share something in common, or we could find a way to have a systematic analysis about all these aspects. Luckily, there is a way to look at these questions. We propose a theory to answer them and give guidance on both hardware and software perspective for future haptic sensor design. What's it about? So in a common setting, high resolution sensors comprise many components and numerous wires. We essentially pursue a way that only uses a few sensing elements and advanced data processing to achieve the same sensing performance. This belongs to a research domain called super resolution sensing. While creating different skin prototypes, we observe that several taxons, the orange dots here, respond to the contact on the soft skin, each of them in a very different way. To understand this more deeply, we closely look at one of such taxons shown on the right here. The taxon has a certain response when we touch directly above it. To keep this particular response, we need a higher force when the contact points are further away. The orange line describes this force distance relationship that we call a taxon value ice line. Along this line, the sensor has the same value, but it describes how much forces are needed for different positions. How can we make use of these ice lines? Consider two taxons and their ice lines. The point where they meet tells us the contact location and force strength, shown in green. However, we always have measurement noises visualized by the blue shaded area. It's caused mostly by the movements inside the wires, inside the DAQs or the accessories. This is typically known as the Johnson-Nyquist noise. Thus, a contact point can only be inferred up to a certain precision, visualized by the size of the dashed square. Comparing of how many points we can distinguish the number of dashed squares to the number of taxons, the orange dot squares gives us a measure of the performance, the super resolution factor omega. So in the end, we aim to design sensors with a super resolution factor as high as possible. The accuracy gets higher when more taxons get or are activated and their ice lines intersect. The spatial distributions of the force of the position and force accuracies are shown on the right. The dashed orange lines here shows the lowest detectable forces, which we call the sensitivity. No localization of contact is possible below this line. With high forces, the accuracy is both higher in localization and quantification of the force strength because more taxons are activated. With these insights, we can start to create sensor prototypes. But as mentioned before, we are always confronted with many design choices. For instance, which taxons should we use? We can use barometers to measure the internal pressure changes if we press the soft skin, or we can use accelerometers, taking the gravity as a reference to measure the surface inclination, or strain gauges to measure the surface elongation, or something else. How thick should the skin be from the mechanical perspective, and how far can the taxons be spaced here? And where should the taxons be positioned within the elastic material? Last but not least, which material is actually appropriate? Which Young's modules or Poisson's ratio or other highest elastic material properties that we have to consider? So all these questions gather together. The answer is all these aspects will affect the ice line shape, where the intersected area changes with the ice line slope. Based on these findings, the proposed theory can be used to give informed answers to all these questions, and then used to guide us to obtain optimal super resolution sensing. With this knowledge, we run an experiment by embedding 6 parameters inside an elastomer, and by measuring the ice line shape and the sensor noise level, we can calculate the best achievable accuracy, sigma p and sigma f, to describe the accuracy. This is from the hardware perspective. We can know that we can achieve this kind of accuracy. And taking it as the best achievable sensor performance, shown as the orange line here, we can evaluate the data processing methods. For example, a machine learning solution is used here. If the performance of the machine learning solution doesn't approach the orange upper bound, there should clearly be some improvements done in the data processing procedure. It can happen in the data collection procedure or the machine learning methods or the data processing methods. As a validation experiment, we place the sensors with different distances. The areas either below the ice lines or have no ice line intersections on both sides have worse localization performance. With larger placement distances, the performance will have a further drop, especially the area with less ice line intersection. Using our theory as guidance, we created a 2D skin using 25 parameters, and we built an automatic test bed to collect data and to train a machine learning model, very simple, to predict the contact location and force strength. We illustrated the precision by letting the test bed stimulate the skin following the points constituting the Minerva picture here. Already for a contact point corresponding to 50 grams, the skin can localize the contact very precisely, shown by the green dots. Almost perfect reconstruction can be obtained by 100-gram contact. The skin can distinguish, in average, more than 25,000 points using only 25 taxons, which means a super resolution factor of over 1,000 we have achieved using the super resolution theory as a guidance.
So Huanbo, so I understand clearly what this theory is telling, right? This theory is saying where to place the sensors.
Yes.
I mean, you had different things that you said which thing to measure, right? And there are different factors over there.
Yeah.
And then there are, where to place the sensors, which you get by the response curve, right? And that tells you how you should arrange the sensors.
Yes.
So for the response curves, I understand what the theory might tell you, right? It might tell you at how far away the sensor should be placed, so you can get a particular super resolution. But how do you choose the material, and how do you choose what you are measuring? Are you measuring the current, or like from a barometer, or I mean, so those choices, how does the theory play in with that?
So like if we have the accelerometers, right? Accelerometers is typically used for like piezoelectric effect that have to measure the inclination, taking the gravity as gravity direction as the reference, right? It measures the inclination of the surface, and then it has an ice line shape, not as this kind of U shape. It has a 2 wing shape right above the top, and all these aspects we have analyzed in our paper, and then we have different sensor types that we use, or the tax or the sensing elements we use.
Okay. Okay.
Yeah, and also the material part, the Young's modules, and it will affect the curve linearly, and also for Poisson's ratio, it will affect the like shear forces, normal forces, the Einstein shape, also in a way that is analyzable.
Okay.
Yeah.
And you also take into account the noise characteristics of these sensors.
Yes. So we measure the sensor noise, and we embed the like individual tactile or sensing element in the elastomer, and then choosing the elastomer, the mechanical structure, and also the sensor type, we can measure the sensor noise, and then it's like constant.
Okay. Okay.
And then we can later like knowing the Einstein shape and then the noise level, we can calculate the accuracy. Like this is an empirical evaluation about the hardware part. Yeah.
Thank you.
Can I ask a stupid question, Huanbo?
Yeah.
So what happens if you just place the sensors at some heuristic distance from each other? Is that enough? Like, have you compared to just like the dumbest heuristic baselines, like uniformly spaced at some, like you just do a little bit of hyperparameter searching in sim or something, and then you just do something heuristic. Like, is that basically, I'm trying to figure out how much does the isolines buy you over just a heuristic?
Maybe I didn't get your question clearly.
I can re-explain. I think so. One thing that you get from the isolines is that you have the ability to figure out how much you should space the sensors, right? Like how far should they be from each other?
Yeah.
Right.
So first we get the isoline like the coverage of them, and this is called like a sensing perception field. It's like, okay, we know the isolines, and then we know that, okay, far away from this region, we cannot like get response from the sensor. So we have to close.
So I guess what I'm asking is that, let's say we were stupid and we decided to not look at the theory, and we just decided to experiment with an heuristic number for how much to space the sensors, and we just validated performance based on some end metric. And we just did a little bit of like hand tuning, right?
Yes,
like how much worse or better do you get, you know?
Yes, we can definitely do that. This is how I get the experience and come to the theory part, because I like design the sensors, running the machine learning pipelines, and then I don't get a good performance, right? And then I'm wondering how can I like design sensors in this way, 10 iterations or 100 iterations to get the performance. I don't know the bottleneck of designing high resolution performance of sensors. So that's why I'm thinking, okay, are there any like a thing that can give us some guidance of designing sensors, not like by like error and try and all this stuff.
I see. So you're just saying when you're designing different sensors with different morphologies and shapes and so on, it just becomes hard to keep re-choosing the values for every one of them.
Yeah.
I see. Got it. Okay, makes sense. Thank you.
So we come to the theory because I made a lot of mistakes, and that takes a lot.
Yeah, sounds good. Thank you.
So maybe a follow-up to that one, but right? I mean, one naive strategy is to put many sensors, right? And that has some drawbacks. So what in your opinion are the biggest drawbacks of putting a lot of sensors?
So it's kind of put a lot of sensors. We need to communicate with them, right? And then this is initial question about robustness. If we have the wires connected to them, and then when the tactile sensors contact with others, and then it will constantly bending, and then at some time it will break. And then if we have like limited space for sensors, right? If we increase the number of sensors, and then we have limit like thinner wires, and then it will break faster than less tactiles, right?
Yeah, and have you also considered wireless sensors, or is most of your work, with wired sensors?
With wires, yes. And wireless sensors is like it's the wireless means like the communication is wireless. It's not mean it doesn't mean that there is no wire in the sensor.
Yeah. So I mean, so if sensors were wireless, do you think the breakage problem would be less? At least, I mean, there's some breakage which happens inside the sensors, and there's some breakage which happens, when the sensors connect to transport the data. So you think the main problem is breakage inside the sensor or breakage in the transportation?
Transportation. Both, I think both, but the transportation is like from my experience is like the most significant bottleneck.
Okay.
Yeah. And also, like, I can draw a summary for this project. So the theoretical formulation and the practical application show prominence for super resolution-oriented sensor designs. And also the theory explains the essential parts aspects for machine learning methods being applied. We don't need to like handful tuning or analyze or do data processing for them, and the machine learning pipeline can simplify this procedure. And also the theory can guide the design of other sensor types and has no geometry constraints. So we further apply this theory to design a 3D fingertip-sized sensor called BaroDome. There are 16 parameters spotted by a spot cone and overmolded inside a soft elastomer. A 5 degree of freedom test bed is built to collect both normal and shear forces on the soft elastomer surface. Simple machine learning models are trained to predict the contact position and force strength. This sensor can also achieve sub-millimeter precision of localizing a contact. But the focus of this project is to analyze how shear forces affect the sensing behavior. So the indenter here probes the surface along the y direction trajectory with normal forces applied. In addition, when applying shear forces along x direction here, the isoline shape changes slightly, while very dramatically for shear forces along y direction. This gives us some like hints that for shear force direct detection, the accuracy will have a drop or will be worse. But a detailed explanation is shown here. Like positive shear forces along y direction here applied at point 1 squeezes the elastomer and activates higher pressure values in the barometer. And thus, less normal forces is needed because normal force is also like squeezing the elastomer. In contrast, at point 2, positive shear forces pulls the elastomer like to create a vacuum pressure in the barometer and thus activates lower pressure value in the barometer. Thus higher normal forces is needed to compensate the pressure value drop. A detailed normal and shear force relationship to activate the barometer sensor is shown here. The sensor has a different response to the shear forces in x direction. So this is for y direction shear force, and this is for x direction shear force. In general, an asymmetric behavior in y direction and asymmetric behavior in x direction. So this is like a message I want to deliver very briefly, but because it's like very detailed explanation needs a long time to explain. So the shape of the isoline surface to describe normal forces, shear forces, and the distance looks like a bow. So how can we make use of them? To deal with the ambiguity, we need to place additional sensors in both y direction and x direction because the uncertainty intersection part is like a 3D volume. Different sensor arrangement layout can be designed for this purpose. So there are also many other fingertip-sized haptic sensors available on the market. One of the most commonly used tactile sensors is BaroDome. BaroDome is a multimodule tactile sensor that uses electrical impedance tomography technique to sense the contact and can additionally sense temperature and high-frequency vibration. It's relatively expensive and hard to maintain spatiality in the long-term run. Both of our BaroDome and the ERTac can supply high-speed contact information, but it's limited to detect point contacts rather than the surface contact. For surface contact detection purpose, most recently, vision-based optic sensor designs have demonstrated a new family of solutions, typically using a high-resolution camera here to see a soft skin from within. This design strategy can realize compact and high-resolution haptic sensing with low cost. Because cameras are nowadays very accessible and computer vision techniques are relatively mature compared to the haptic techniques. One representative vision-based haptic sensor is GSI. It has a thin reflective membrane or coating on top of a transparent elastomer layer, supported by a flat acrylic plate. Lighting parallel to the surface allows tiny deformations to be detected using photometric stereo techniques. Another representative sensor is called Tactile. It uses a hollow structure with a soft shell, and it detects deformation on shell's inner side by visually tracking the markers, the white markers here. Other variants using similar techniques are available, as shown here. Most of these sensors have relatively flat sensing geometry. Compared to the 2D flat geometry, a 3D sensing surface can enable robots to feel all sides of their body parts, like a human skin, which lets them work better in messy real-world environments. So thus we are motivated to design a vision-based haptic sensor with a compliant 3D sensing surface. It has a name. It's called Insight. Insight is a vision-based haptic sensor that uses a camera and a structured lighting system to detect external contact happened on a soft hollow elastomer. Insight constantly records images from inside using the camera, feeding these images and a reference image into a trained machine learning model. Makes it possible to estimate the force distribution all over the surface. Each pixel in the force prediction map has 3 values that indicate the force strength in 3 directions. In a force visualization on the right, each point corresponding to 1 pixel in the force prediction shows the force distribution of the contact in both normal and shear directions. There are 4 key design components making Insight work properly: the soft rigid mechanical design of the shell, the single camera imaging system, an automatic data collection procedure, and also deep learning algorithms are used behind the scenes to create or to design such a cheap, robust, and easy to use device. Our hybrid structure of a soft elastomer enclosing a stiff metal skeleton ensures high sensitivity and robustness. The soft elastomer is for detecting light contact with high sensitivity, and the metal skeleton is for holding the elastomer's global shape and sustaining high impact forces. We use a AVD and a collimator to create structured light. The structured light forms a light cone inside the enclosed volume. Each voxel inside this volume has a specific color code with 3D information. External contact moves the elastomer from one color zone to another. Together with the shading phase, the camera can detect the 3D deformation of the surface from a 2D single image. As shown on the right figure, mimicking human fingerprint, we also added ridges to the surface to amplify the mechanical deformation and have the system recognize the directions of the surface extension. We designed a testbed to stimulate sensor in a controlled way with both normal and shear forces over the entire 3D sensing surface. It's in my bag. It's still collecting data for other purpose. The data is used to train a deep neural network, which is then used at runtime to make force inference. Right. The sensor can localize the contact with a precision up to 2 millimeters. A force of 100 millimeters is sufficient for reliable detection. Notice also here how the shear forces are quantified for multiple contacts. This is 4 contacts situation. Yeah. The sensor can also track dynamic contact on the surface and detect the detailed shape of an object. So in summary, Insight has an overall spatial resolution of 0.4 millimeters, a force magnitude accuracy of around 30 millinewton, and a force direction accuracy of around 5 degrees. It can sense its safe orientation with respect to the gravity direction and detect detailed shape of an contact object. It has a low cost for the essential components, around $100, and inside is tested to be very robust by many children in our Institute Science Open Day. And compared to other sensors, our inside sensor has an outstanding performance with the largest 3D sensing area and competitive accuracies. So we're also pretty happy to see that our research has attracted a large amount of media coverage and has potential impact in both academia and industry. That's all for the introductions of the sensors I've developed during my PhD study. And in summary, when designing machine learning-driven haptic sensors, we need to first have a systematic analysis about the whole implementability and should not be trapped into an individual state. We need to jointly consider the hardware implementation and the data collection, as well as the data processing steps. For the hardware part, I would suggest to prioritize the robustness over the accuracy. The data can be either acquired by a designed testbed, synthesized using finite element models, or even collected in a fully integrated robotic system with lifelong learning procedure. And regarding the algorithms, we need to consider the generalization property of the trained machine learning models and think of building pipelines that can merge data from different data sources. And also, we have to consider different sensors have different sensor properties. Thus, we need to adapt the machine learning pipeline to them respectively. This is the take-home message that I would like to deliver in this talk. I hope you will like it. So yes, in general, I have interest in the following topics: and designing haptic sensors for robots, designing soft robots with sensing capability, and designing haptic sensors and actuators for robots. Yes, and thank you very much for your attention, and I'm looking forward to answer any question you might have.
So let's thank Huanbo for the wonderful talk and enlightening us about all the wonderful touch sensors that he has built. So thanks, Huanbo.
You're welcome.
Let's also thank Tao for organizing this seminar. And now I think we can take any more pending questions.
How much smaller do you think that the insight sensor can get with future iterations?
You mean the force detection or the size of the inside sensor?
The size of the sensor itself, how much smaller can it get and still be able to fit all the hardware you need?
The limitation is like the camera and how small the camera we can buy off the shelf, and also the field of view. If we want to have a large field of view, we have like to buy a fisheye lens to get enlarge the viewpoint. And currently, we are designing a sensor that has the size of my fingertip of my thumb. This one, yeah. But smaller, I don't know yet.
Awesome, thank you. And also, how much is the delay between when you touch it and you actually sense that in the controller? And then also, at what frequency can you sample? And how does this compare if you don't use machine learning?
Okay, so the first prototype, the first version of our inside sensor use a Raspberry Pi camera. It has perceive the images at 60 frames per second, and then streamed to our PC at 10 frames per second, and then the inference takes inference is running in real time, gives us 8 frames per second force map output, and the delay would be like the 8 frames per second this time domain. And then the second, we have designed a second sensor with a smaller size, and the camera has 90 frames per second. It's a USB camera. It can be directly plugged into a PC and to run the inference at real time. Currently we have achieved 60 frames per second inference. Yeah.
Awesome, thank you.
So maybe one question on the technologies that you were using. So like on the ERTac on the left, right? That is not vision based, and Insight seems to be vision based.
Yeah.
So do you think we could replace vision based sensors with something more like ERTac in the future, but still get what you get in Insight? I mean, the reason being, it all depends on the camera. You can't make the camera much smaller. And then you have to put in the optical system, right? So which really constricts how small you can go.
Yes. So ERTac is, it depends on how like we arrange the resources, how like we design the robotic arms or robotic bodies. So the ERTac is mostly for covering directly, like I have a robot and then I just cover the surface with the ERTac. That's that. And then for Insight or for the BaroDome, we have to redesign the fingertip size and then arrange the wires and all these kind of things. So it depends on how we arrange our resources and how we want to design rebuild the platform or build the platform based on the original hardware part.
And then maybe like a flip question. So you talked about how sensitive these sensors are, right? So which is they can measure very small amounts of forces.
Yeah.
But what is the biggest amount of force they can sustain, without breaking? So yeah, for example, right? I mean, if you were to put maybe touch sensors on a quadruped or a biped, right, which is moving, but it also stomps on the floor.
So yeah, so first is like the operation like force range. So for this one, the HapDef, this part, and then it is designed to sustain single contact with 35 Newton. And our Poppy robot is around 3.5 kilogram. So I think this is how we decide the operation range. We think single contact, if the robot is standing on the knee and then it contacts the surface, it can hold its own weight. And also for the inside sensor, we have a soft elastomer for detecting the soft contact. But we have printed a metal beam here. Maybe I stop sharing my screen and you can see better. Good. So here, this is the metal beam that we printed. It can sustain like 35 Newton also on our fingertip. So it's quite robust. And then if this is made of aluminum, it's 35. If this is made of metal steel, this part is metal steel, it can go for 100 Newton. So it depends on how we choose the material. Yeah.
Right. Great. Any more questions from anyone?
Yeah, so I have a question on the inside finger. Sorry, can you hear me well?
Alan, I don't think we can hear you. So
let me change the device or like someone else can. Yeah, so I can also ask offline.
sorry, what did you say, Alan? I mean, if you want to type your question, you can type your question because your voice is a bit muffled. So we cannot.
Yeah, maybe you can type in the chat channel and then I can read.
So while Alan is typing his question, any more questions for Huanbo? No. Okay.
Why did you choose a hollow gel metal frame? So Alan asked a question, why did I choose hollow gel and metal frame vs solid gel? Because we want to keep this the finger as light as possible. And also if we have a solid gel and then the gravity effect will pull it has an inertia effect more obviously, and then we cannot tell if this is the contact caused by, if the deformation is caused by the contact or by self-weight. So two purposes. One is keep it lightweight, and the second is to keep less ambiguity from either contact or gravity effect.
Great. So I guess if there are no more questions, let's thank Huanbo once more. So thank you, Huanbo.
Also, thank you for your